Okay, we're live. Google Hangouts is working again. Okay, so this week, rather than talk about Gaussian processes, which are very flexible models, sometimes called Bayesian non-parametric models, that have so many parameters that they're called non-parametric. Those are very useful, and most of the innovation on them is happening around Stan and the Bayesian community. But I think we're better served trying to review and maybe extend on some of the ideas from earlier in the semester for today and for Thursday. So this week, contrary to what was on the syllabus, is really going to be more of a review week. And we can start by reviewing the fact that we're at Columbia talking about Stan. We're paid to work on Stan sometimes. Columbia considers that a conflict of interest. So I think it's important to understand a little bit about the history of a lot of these ideas, because you need to understand the problems that people in that historical era were attempting to solve when they developed, this or that method, and are those considerations still true today? So Thomas Bayes did figure out how to get a beta posterior distribution from a beta prior and binomial data sometime around 1750. He didn't figure out Bayes' theorem or conjugacy or whatever in general. He didn't even really tell anyone that he figured this out before dying, but one of his friends found it, the paper that he'd written, and sort of pushed it along. A guy named Simon Lepulse in France independently derived what we would consider today Bayesianism in the 1800s. But somewhat curiously, he wasn't that committed to it. So after he'd done all this work to kind of derive a bunch of this stuff, he, kind of went back to non-Bayesian methods in his empirical work. Nevertheless, what Lepulse had done was sufficiently Bayesian for Fisher to criticize it. Fisher is actually the one who invented the word Bayesian and Bayesianism, which he considered to be an insult, among lots of other insults that he had to say to various people. And he derived maximum likelihood around 1922, series of papers. Wasn't until a little bit later that Neyman, along with Egon Pearson, developed the idea of a confidence interval. So that came a little bit later, and those two things together, even though they're kind of incompatible, and Fisher and Neyman couldn't be in the same room as each other, kind of morphed into what we call frequentism today. There was a lot of stuff intended for quantitative methods during World War II, and we learned or saw first week or so all the stuff that Alan Turing did using Bayesian methods, even though he didn't really call it that. They weren't too caught up on what things should be called or, academic battles and things like that, because they were just trying to survive the Second World War. As part of the whole World War II thing, physicists working on the atomic bomb developed Monte Carlo methods, late 1940s, 1950, 1951, stuff like that. And they had sort of figured out this idea of what was later termed Metropolis-Hastings algorithm for estimating probabilities of stuff, because both Metropolis, or certainly Metropolis, I think Hastings came along later, was, part of the Manhattan Project and stuff like that, along with Stan Ulam and the Tellers and Rosenbluth and people like that. Anyway, physicists had this idea of how you could use simulation to estimate probabilities, but no one outside of physics that wasn't, on the Manhattan Project understood what that was at all. Didn't put it on here, but around the same time, late 1940s, 1950 or so, is when social science, as we would recognize it today, got its start. The things before World War II that happened under the realm of like social science departments really weren't particularly scientific or social. So in particular, the problems that Fisher was working on were not social science problems at all. That was sort of picked up by other people later that said, well, mathematically speaking, you could use the methods that Fisher derived, maximum likelihood and so forth, for social science problems once they invented problems in the social sciences to attack scientifically. But that wasn't Fisher's intention, and so there's no real logical argument as to why those would be the optimal sort of methods for doing social science research problems, because that just wasn't on Fisher's or anybody else in the 1920s radar. So we had social sciences developing around the same time as Monte Carlo methods, but social scientists didn't know anything about Monte Carlo methods because they were only written in physics journals that social scientists didn't read. Then the Guimond brothers made the connection, derived Gibbs sampler in 1984. There was another important paper I didn't list on here about 1990 that was actually in the Journal of the American Statistical Association journal. Guimond and Guimond were interested in image restoration, which is still like pretty far outside of social scientists. But anyway, Gelfand and Smith in 1990 at least sort of gave a review article that was in JASA. And some social scientists read that article. Many more have read it today. And so a few years later, the Bugs project got started. I think that was actually in 1993 or so when it first got started, but it just crashed for a couple of years. By 1995, you know, up until it had a pretty good run to 2005, Bugs, and then later WinBugs, which came around 1999, 2000, something like that, was a popular program that did Gibbs sampling when it could. It had fallbacks to things like Metropolis steps, slice sampling, when it didn't recognize what full conditional distribution it was drawing from. And this tended to produce numbers. It was doing stuff by MCMC. They had Bayesian interpretation. We didn't understand as well as we should have at the time that these numbers that we were getting, the averages of these numbers weren't particularly representative of the true posterior expectations we were trying to estimate, because for a lot of data sets, the Gibbs sampler implemented by the Bugs family wasn't moving around the posterior distribution efficiently enough to get, you know, reliable estimates of these things with a finite number of draws. It was hard to get things to converge. Even if you did, the chains mixed slowly, so you sort of average the same number over and over and over again almost. And in a lot of situations, it wasn't a good estimate of the posterior expectation you were trying to estimate. WinBugs is still sort of disturbingly used today, even though the Bugs people have basically said WinBugs is no longer actively being developed. These ideas are being pushed by like one person, one developer each, approximately one developer each, in the OpenBugs and the JAGS packages, which implement similar ideas along the lines of, you know, doing Gibbs sampling when it's possible, doing something else when Gibbs sampling is not possible. And in 2011, 2010, when we started developing STAN, it was sort of in reaction to the limitation of the Bugs family stuff. It wouldn't converge fast enough. It wouldn't mix well on problems, particularly problems in social science, particularly problems in political science. And so Andrew Gelman was interested in developing software that would be appropriate for those sorts of problems. And Stan has evolved pretty rapidly since then. Matt Hoffman came to Columbia on a postdoc, worked out the nuts algorithm, and then we had an algorithm to base, you know, the Stan language, the Stan library, the Stan R packages and stuff around. A lot of things took off from there. And today, you know, Stan's algorithm, the nuts thing, has been copied a few places. PyMC3 is one of those. But it is basically, among people who have looked at this sort of thing, the best general purpose MCMC algorithm for differentiable problems is the nuts algorithm. You get most efficient movement through the posterior distribution. The estimates that you get from that are more reliable than any other general purpose MCMC thing. There's some specialized cases involving discrete parameters and stuff like that that Stan can't do. But for most models, they either already are continuous in their unknowns, or we can rewrite the model in a way so that they only have continuous unknowns. That may be a little bit tedious, but Stan really is the best technology for drawing from differentiable posterior distributions, and it's sort of necessary to have technology that good in order to do the sorts of models that we originally couldn't do with things like bugs. Big hierarchical models, for example, just to take one in the social sciences, but there are many others, and many others outside the social sciences. So it actually works a whole lot better than we thought it would in 2011. So in that sense, we kind of got lucky, but there's really not a whole lot of point in learning how to do MCMC in 2017 in anything other than the Hamiltonian Monte Carlo algorithms that are implemented in Stan. All right. So, you know, we learned a lot of probability theory and stuff like that, different ways of calling Stan, but it really is not just a Bayesian class, but a Stan class that we're, you know, trying to get through the last few days of. All right. Questions about that? No? All right. So going back to the sort of 1920 or so, there's a class of PDFs that can be written like this for some random variable x, conditional on a vector, could be a scalar parameter eta, that can be written involving 4 terms. Some function that's scalar h of x, positive, some function of a vector eta to a scalar g of eta that's also positive, and then e raised to an exponent that involves the vector product of eta and this function of the data s. That function of the data s is a vector function of the same length as eta, but both of those could be scalars, in which case that's a scalar function as well. So we've seen e raised to the power of something a lot, and it turns out there's a lot of PDFs and PMFs that can be written in this form for some choice of hg, eta, and s. So why do we care about this? Well, for n conditionally independent observations, independent conditional on eta, then the likelihood for an entire sample, remember a likelihood function is a function of eta, so we can consider any term that doesn't depend on eta to be a constant and drop it. So the h of x term doesn't depend on eta, it goes away. And so we get a likelihood that's proportional to the g function raised to the power of n, because you have that n times if you have n conditionally independent data points. And then e raised to the power eta times s, where s is known as the vector of sufficient statistics, and the vector of sufficient statistics for a sample is just the sum of the sufficient statistics for each observation overall in observations. And the reason why this s function is called sufficient statistics, it's a function that depends on the data only. But if you have S, then the likelihood only depends on the data through the S function, because the H function drops out. It's just a constant. So the only place where eta and S touch each other is in the exponent of this E term. So what's so great about sufficient statistics? Well, they make the math a lot easier. So if you take the logarithm of that likelihood function, little l, you can write it as the E goes away. And then if you differentiate that with respect to eta, the second term, eta transpose times S, that's just S. So we're left with a relatively simple first order condition that the maximum likelihood estimator has to satisfy, namely the negative of the derivative of the g function with respect to eta divided by the g function is equal to 1 over n times the vector of sufficient statistics. So the maximum likelihood estimator eta hat satisfies that system of equations. And you're like, okay, well, maybe for a particular form of g function, I could solve that system of equations, but I still have not really gotten to why it's important to state the problem in this form and derive the sufficient statistics. The reason why that is because as the sample size goes to infinity, the central limit theorem, which is really the essence of the frequentist approach to statistics, implies that 1 over n times S, which is just an average of the sufficient statistic, and averages converge in distribution to a multivariate normal. And particularly, it's the multivariate normal for that negative ratio evaluated at the true eta, and it has some variance covariance matrix here written sigma inverse, and sigma can be written as n times the negative of the second derivatives of the term on the left in the log likelihood. So it's the second derivative of the log likelihood. That's a matrix. You multiply it by n, you invert it, you get the variance covariance matrix of the maximum likelihood estimator over repeated samples. Remember, the frequentist estimator, all this stuff is to be evaluated. What if you were to do this study, over and over and over again? What would be the distribution of the maximum likelihood estimates for large n? The distribution of the maximum likelihood estimates over studies would be multivariate normal with these constants here. And sigma inverse is known as the Fisher information matrix, which Fisher named after himself in order to sort of capture how much information about the unknown parameter is provided by the data. It has to do with the second derivatives, which pertain to the curvature or lack thereof of the log likelihood function. So this is really important because the central limit theorem is, slightly magical. There's lots of things that sort of converge pretty rapidly to, or lots of averages that converge pretty rapidly to normal distributions, provided that the thing that you're averaging has a finite variance, and provided that it's the data generating process for it is not too skewed. Then 15, 20 observations, if they're independent of each other, is really enough in order to make the sampling distribution of some of these estimators be normal. And back in 1920s or so, that was like a big sample. Certainly not the case today, but by constructing the problem in this way where they could leverage the central limit theorem, they know that 1 over n times S converges to a multivariate normal, so anything that's equal to 1 over n times S, namely this ratio involving the maximum likelihood estimates, is also going to have a multivariate normal sampling distribution. So we can take the diagonal elements of our estimate of sigma inverse, and those are variances. We can take the square roots of them. Those are standard errors. We can divide test statistics, the point estimate divided by the standard error to get Z statistics. We can look in the tails of the Z statistics to get p-values. We can use the standard errors to get confidence intervals. All the important ingredients of frequentist inference. In order to do them, you have to know the sampling distribution of your estimator across studies. And if you formulate the problem this way, the sampling distribution is going to be normal. Another important characteristic of maximum likelihood estimates is that if you do one-to-one transformations of eta, the transform thing is just a reparameterized maximum likelihood estimate. So you can change the parameterization after you found this in order to get maximum likelihood estimates for a different parameterization or something like that. It's pretty straightforward math. Note that one-to-one transformation business does not hold for a posterior mode. It holds for a maximum likelihood estimate. If you do it right, it holds for a posterior mean. It does not hold for a posterior mode, which is among the other reasons why Bayesians shouldn't really care about posterior modes, is because that depends on which of several equivalent parameterizations you use for the problem. But that was something that we discovered much later. In the 1920s, which is where we're thinking about this, frequentists such as Fisher chose to work on problems that could be coerced into this class, where the likelihood has this form called the exponential family or the exponential class, because that was the only thing that could be done in the pre-computer era to make the math tractable. You could otherwise write down likelihood that didn't fall in this form for the exponential family, but you couldn't really obtain maximum likelihood estimates. There wouldn't be any closed form solution, etc. And so this form was really necessary in order to do maximum likelihood estimation before there was computers. And Fisher, who was good at many things, getting along with other people was not among them, but he was really good at coercing distributions, statistical distributions, into this form. You have to sort of choose the H and the G and the S carefully, and figuring out what the sufficient statistics would be to do a ton of problems that you could put into this form, and then do the sampling distribution of the maximum likelihood estimator, knew how to get these answers analytically, and knew that it would work reasonably well as long as the data generating process that generated the sufficient statistics was not too skewed. You could get by with samples of 30 or whatever. But those were the problems that Fisher was like a biologist, certainly not a social scientist, was interested in trying to figure out, and made a fair amount of progress just within this slide, doing that over and over again. Questions? All right. So what are the limitations of this? If you click on this link, there's a ton of distributions that fall in the exponential family. Most of the ones that you've heard of, some of which you may have not heard of. But it's certainly not all distributions. Also, the natural parameterization is oftentimes pretty unnatural. You can work in terms of theta with the parameterization you're more familiar with, but the math is going to be more difficult. But basically, this really only works for one parameter or two parameter distributions, and oftentimes you have to assume that one of the two parameters is known, is fixed, is a constant you're not estimating in order to make the rest of the distribution fit in the exponential family. So about the most advanced thing that can be done within this framework is generalized linear models. That wasn't really figured out until the early 1970s, but generalized linear models are connected to the exponential family directly. That's why the family argument to the GLM function in R is called family instead of likelihood. It only works with likelihoods that can be fit into the exponential family form. Other distributions that are not in the exponential family, if they have sufficient statistics, the number of sufficient statistics to keep track of grows at the same rate as n. So outside the exponential family, you're usually going to have to resort to numerical solutions to obtain maximum likelihood estimates. And if you're not leveraging sufficient statistics and averages of sufficient statistics and the fact that averages obey a multivariate normal distribution, then the estimates that you get when you do maximum likelihood numerically are not necessarily going to have the decent finite sample properties that maximum likelihood estimates that you can obtain analytically or otherwise using the exponential family have. So there's really no guarantee that any finite amount of observations is going to be adequate for you to get this multivariate normal sampling distribution that's assumed by the standard error estimate, the t statistics or z statistics, p-values, confidence intervals, etc. For any finite number of observations, those may be completely wrong or completely different than what their asymptotic versions are for sample size going to infinity. And so maximum likelihood estimation during Fisher's day kind of got a reputation for working well, but people sort of took the fact that it worked reasonably well for problems that could be fit using exponential family form to situations in which you can't leverage that fact anymore, and didn't realize that the sampling distributions they would get from finite samples were going to be less good than what they could got decades before there was computers, when they had to use analytical methods, and they had to do it on problems that were so simple that admitted an analytical solution, again, always using exponential family forms. Questions about that?
What was the second line about Taylor's?
Yeah, so we'll see this in a second. The natural parameterization is usually not used by anyone in nature unless they're trying to derive the sufficient statistics. So it involves weird parameterizations. So let's say we have a likelihood in the exponential family, so it has this. It can be shown that every likelihood in the exponential family has a conjugate prior that's going to take a similar form. So a conjugate prior for eta, which is a g function raised to the power nu, e with a product eta times chi, and some normalizing constant in the denominator that depends on nu and chi, but not eta. So if we have a conjugate prior and an exponential family likelihood, then the posterior distribution is going to be in the same family as the prior, but with updated parameters. And we get a general form of something that we've seen many times, that if you multiply those two things together, you get a posterior distribution in the same family as the prior with new parameters, nu star and chi star, where nu is equal, nu star is equal to the original nu plus the number of observations, and chi star is equal to the original chi from your prior plus the sufficient statistic from the sample. And that means you can interpret nu as the number of prior observations. Those could actually be prior observations from a prior study, or they could be hypothetical prior observations, or they could be, you know, prior observations that are kind of somewhat related to the phenomenon that you're studying, but not exactly. Like we did in the case of Ebola, we had, you know, some number of observations on monkeys who received the drug before we had any observations on humans. So nu could be equal to the number of monkeys in the study, or if you're not super confident as to whether monkeys' immune system is going to react the same way as a human, you could say, well, I'm just going to cut that in half or something like that. And then chi can be interpreted as the value of the sufficient statistic for those actual or hypothetical new prior observations. So if you're using the exponential family, there's going to be a conjugate prior. And even in the 1920s, you could have derived the posterior distribution in the same family. Also, for any fixed nu and chi, as the number of observations goes to infinity, the difference between nu star and n goes to 0, and the same thing with chi star and s of x. So the posterior PDF is going to converge to the likelihood divided by the normalizing constant. The normalizing constant is not a function of eta, so the mode of the likelihood is going to be the same as the mode of the posterior for large samples. And if you do a Taylor approximation of the log likelihood at the maximum likelihood value, then you get a kernel of a multivariate normal PDF that involves the maximum likelihood estimates eta and sigma inverse. And that's just the kernel of a multivariate normal PDF. And so the posterior distribution is approximately going to be multivariate normal. And then that's the same multivariate normal distribution that the sampling distribution of the maximum likelihood estimator is converging to. So even in the 1920s, for every problem where they could get a maximum likelihood estimator, they could get a posterior distribution that was conjugate to a prior distribution if they chose the prior distribution from the class that was, conjugate with these likelihoods from the exponential family. They chose not to do so because Fisher was convinced, and convinced many of the other statisticians of that era, that the Bayesian approach was wrong. It was objective to use the maximum likelihood estimator. It was subjective and all sorts of other things to be using priors. But it could have been figured out at the time that, for finite n, the posterior distribution is this, and only for large n is that posterior distribution going to be well approximated by a multivariate normal. But it didn't really take that large of an n to make that happen if you're using exponential family likelihoods and conjugate priors. So you could sort of get an approximation to the posterior distribution from taking a frequentist maximum likelihood approach, even though mathematically there was nothing stopping you from getting the correct posterior distribution for any finite sample. Questions? Okay. So again, thinking about ourselves in like 1920s or so, in this approximation on the previous line here, multivariate normal, it's just a simple Taylor approximation, neglecting all the higher order terms. But in this setup, the higher order terms quickly become negligible, and the sampling distribution of the maximum likelihood estimator is approximately the same as the posterior distribution you would get if you used conjugacy. Fisher did not do that. So Fisher, as I said, chose to work on problems where the multivariate normal sampling distribution of the maximum likelihood estimator was a good approximation to the posterior distribution, assuming a conjugate prior. But Fisher didn't really recognize this. He just thought, maximum likelihood estimation was doing a good job. But the reason why maximum likelihood estimation was doing a good job on the problems he chose to apply it to, which were the only problems that could really be done at that time using exponential family, was because it yielded an answer that was close to a Bayesian posterior distribution. And actually, Bayesian analysis works well in finite samples. But Fisher and other people claimed that maximum likelihood estimate worked well, even with relatively small sample sizes. And then in 1960 or so, when computers became more widely available, people started applying this numerical maximum likelihood estimation to problems that couldn't be coerced into exponential family form. And so in 1924, he made one of many inflammatory statements about Bayesianism, that it was founded upon an error and must be wholly rejected, even though maximum likelihood estimation was a close approximation to a posterior distribution when you only work on the subclass of problems with exponential family likelihoods. So there's really a disconnect between what Fisher thought he was arguing against and what he was doing, which a number of people pointed out. And finally, by 1959, Fisher wrote, well, the more I consider it, the more clearly it would appear I've been doing almost exactly what Bayesian had done 200 years earlier. But he still had this sort of weird idea that Bayes was a frequentist. Really, we don't know a whole lot about what Bayes was or was not. He was a minister. But because no one even heard about his paper until after he died, there was no opportunity to really ask him questions about like philosophical issues about probability and stuff like that. So when Fisher was going on about Bayesianism, he really met Laplace and people like Jeffreys, Keynes, etc., who were more contemporary, who were sort of applying this idea of, well, we're updating our beliefs about stuff like that. He thought Bayes was not into belief updating. He sort of imagined Bayes as like doing an infinite number of trials to figure out what his prior distribution would be, and then using that probability distribution that you get from an infinite number of trials for the prior, update it once with the likelihood, even though like updating it with one piece of data after you've already done an infinite number of experiments wouldn't change your beliefs about anything. So it was a weird caricature of Bayes and Bayesianism, but it caught on with the help of the confidence interval thing that came from Neyman and Pearson, and from 19 whatever to about 1990, there really wasn't any Bayesian stuff done of importance in the social sciences. Like in the book that you read before the semester started, there was stuff in insurance. Governments would use Bayesian inference, but university research was basically entirely frequentist. Textbooks were entirely frequentist. Classes were structured around the frequentist approach. And even today, there's not a whole lot of people who are out there arguing, well, the frequentist view of probability is the most appropriate thing for stuff like social sciences. There's a few, but there's not the same sort of thing that Fisher and his friends, if he had any friends, were talking about in the day, where they were really arguing that the frequentist approach to probability was the objective one and the Bayesian one was evil. You don't hear that same sort of thing today, but nevertheless, overwhelming number of people applied people are using frequentist methods because that's the only thing that they're taught. So it's not like, the Wooldridge book, whatever, has like a big section or whatever saying, well, frequentist inference is the right way to do econometrics. Or even a small section saying, well, frequentist is one way to do econometrics, but there's this whole other way called the Bayesian approach that we don't have time to talk about in like one semester, but you should probably take a class on it. The Bayesian approach is not mentioned in introductory books like Wooldridge and lots of other textbooks in econometrics and statistics at all. So it just doesn't get taught. Even though for a lot of problems, it's the appropriate one, and it's reasonably feasible to do today now that we have STAN technology. So just some math for a review problem that you can walk through more slowly. So there was a question about this natural parameterization. So if we have a Poisson likelihood and a gamma prior, the natural parameter is eta, which can be thought of as the logarithm of mu in the Poisson distribution. So we can write the Poisson PMF like this, 1 over x factorial, e raised to the power negative mu e to the eta, where eta is log u. So this is equivalent to e to the negative mu. And then e eta, which again is log u, multiplied by x. If you make the substitutions, that's equivalent to the Poisson PMF that we learned earlier. And in the Poisson case, the sufficient statistic is merely x. So we get a likelihood that sums all that together. If we choose the reparameterization, eta is negative of the rate parameter in the gamma prior, and chi is alpha minus 1, we can get a parameterization of the gamma prior in terms of, or it's a reparameterization of the gamma PDF that we're used to if we multiply by the derivative of mu expressed as a function of eta in order to do the change of variables. So what is the derivative of mu with respect to eta? Okay, what is mu as a function of eta? What?
Exponential, right?
Right, so e to the eta is equal to mu. So mu as a function of eta is e to the eta. What is the derivative of mu with respect to eta? E to the eta. So I had to multiply by e to the eta in order to get this expression on the right, which parameterizes the gamma in terms of nu and chi. So we apply the conjugacy thing. We get posterior PDF kernel that's proportional to e raised to the nu star times e raised to eta times e raised to the power chi star times eta, where nu star is equal to nu minus n and chi star is equal to chi plus 1 plus the sum of the x's, which is the sufficient statistic for the sample in this case. So if we want our posterior distribution, which is gamma, to be in terms of the more familiar parameters alpha star and beta star rather than nu and chi, we have to take our posterior PDF in terms of nu star and chi star and multiply by the derivative of nu with respect to mu. And what is the derivative of nu with respect to mu? Yes. So eta is equal to log mu. If we differentiate that with respect to u, it's 1 over mu. So there's this 1 over mu term that I had to incorporate in. Otherwise, we can just make the substitutions for alpha star and beta star, and we get the posterior PDF for the gamma in the gamma form that I think we worked out before, like a month into the semester, where alpha star is equal to alpha plus the sum of the x's, and beta star is equal to beta plus n. And so there's a 20 or so conjugacy problems that we could work out pretty much just like that, where we're going to get some parameter incremented or some hyperparameter incremented by the number of observations, and the other hyperparameters incremented by some sufficient statistic, like the sum of the x's. All right. So these days, it's not important to use conjugacy. Stan doesn't care. So that frees you up to express your prior beliefs, not using the gamma distribution if you don't want to. You could use the log normal. If you use the log normal, you're not going to get this analytical solution to the posterior distribution, but you could get a numerical MCMC solution in Stan much faster than you could work out the math to get a posterior distribution from the gamma. So in a way, that's good. It gives us more options for expressing our prior beliefs, but working through conjugacy problems is still good for providing intuition as to how conditioning on the data, in this case, a vector of observations x of length n, updates our beliefs about the parameters eta. In the case of conjugacy, our beliefs stay in the same distribution. So they start out with a gamma prior, end up with a gamma posterior when we condition on data that is distributed Poisson. So the gamma stays the same. The family of the prior and the posterior stays the same. It's just we have different hyperparameters after conditioning on the data, alpha star and beta star, whereas before we saw the data, our beliefs were characterized by a gamma distribution with shape alpha and rate beta. So this idea of Bayesian updating, you know, you could do it for the first in observations and update your beliefs, and then get another in observations, update your beliefs. You'd end up in the same gamma posterior as if you got all the data at the same time. So that's useful. But you know, these conjugacy examples really drive home the idea of Bayesian updating, Bayesian learning about the unknowns. In this case, eta, which is, or mu, which are one-to-one related to each other. All right.
So that affects, and the first line is the PDF, the PDF data below in the second line. That's the likelihood. The F data.
Yes. So before we see the data, we can think of X as a random variable, and it has a Poisson PMF. After we observe n actual X values, the likelihood is not a function of X because X is a constant. We're only evaluating it our sample X. The likelihood is considered a function of the unknown parameters, eta or mu, depending on how you parameterize it. So this top line says X conditional on eta is Poisson. A likelihood function is not a PMF or a PDF. This is a PMF for X. The likelihood function takes the same form, but we're thinking of it as a function of the unknown eta or mu, depending on how you parameterize it. And that is a very important distinction that Fisher certainly emphasized, but something that's like lost on a lot of social scientists, the difference between a likelihood function, which is a function of the parameters, and a PMF or PDF, which is conditional on the unknown parameters. And, you know, thinking about how those get used. In particular, the maximum likelihood estimate isn't the estimate of the parameters conditional on the data, because the likelihood function isn't a PDF for eta conditional on X. It's just the same as the PDF for X conditional on eta, reinterpreted in a different way. All right. So if you knew what to say for alpha and beta, and you were comfortable using the gamma distribution to describe your prior beliefs about mu or eta, depending on how you look at it, you could, you know, work out this problem. So how will we choose alpha and beta? And this is one of those things that sort of occurred to me in the last couple of years. There's a lot of people who say, like, you know, I don't know what to put for the priors on like any of these things. I just don't know. But in almost all cases, that confuses being uninformed about the parameter you're talking about, mu, which people do in particular context at least have a rough idea about. So they know something about mu. They're not completely ignorant about what mu is. What they're ignorant about is the gamma distribution. They don't know how to use it to express what they do know or believe about mu. And that's different from having you know, uninformed prior beliefs or non-informative priors or weakly informative priors. That all refers to the strength of your beliefs about mu. Being unable to express your beliefs, whether they're weak or strong, in terms of probability distributions is not, it's just lack of practice with probability. And it's something that you can be better about. And in this day of age, even if you don't really know what you're doing, Wikipedia ought to get you there. So anyone, no matter how clueless they are about the gamma distribution, can look it up on Wikipedia and find that the mode of the gamma distribution is equal to alpha minus 1 over beta. And so that implies beta is equal to alpha minus 1 over the mode. And if you read down further in the Wikipedia, there's an expression for the approximate median, alpha over beta times 3 alpha minus 0.8 divided by 3 alpha plus 0.2. You just substitute that expression here, and now we have a somewhat complicated but not that complicated expression for the median of a gamma distribution in terms of alpha is the only unknown. Ostensibly, you know a guess for the mode. So if you can go onto Wikipedia and find these formulas, if you can articulate what you think before seeing the data is your best guess for mu, and that's the prior mode, and you can articulate the value of mu such that you think there's a 50% chance that it's lower, a 50% chance that it's higher, that's the prior median. And if you can specify those two things, you can get two equations in terms of two unknowns, alpha and beta, and you know your prior mode and you know your prior median for mu, that you can then solve for alpha and beta. The expression for alpha comes up like this. Given a solution for alpha, you can immediately work out what beta is just by plugging your solution for alpha, subtracting 1, dividing by the mode. All this does presume that alpha is greater than 1, because that you need for the existence of the mode. But I didn't even solve those two equations myself. In these day and age, you can just go on the internet, particularly to the Wolfram Alpha site, type in a system of equations, and it will tell you the solution. So to say, like, I don't know how to express my beliefs in terms of a gamma distribution means either you can't work Wikipedia, or you can't work Wolfram Alpha, or you can't really say for yourself what you think is the best guess and the over-under value for mu. But if you're actually substantively doing a study, you ought to be able to say, at least roughly, what the prior mode and the prior median are, solve for values of alpha and beta that are consistent with those two beliefs, and away you go. And that works even if you were using the gamma prior with some other likelihood that isn't conjugate with it. You could use this approach to figure out what alpha and beta are consistent with your prior beliefs about this parameter in terms of a gamma distribution. So these probability distributions are really just a language for expressing your beliefs about stuff, whether it's before observing the data or after conditioning on the data. Question? Yes.
What's the rationale for gamma distribution? What's the rationale for gamma distribution?
Okay, so historically, the rationale, at least from a Bayesian perspective, is gamma is conjugate with Poisson and some other stuff. So it's sort of the most likely thing to be conjugate. You could work out an analytical solution. A deeper answer is that the gamma distribution is a maximum entropy distribution for some constraints, which means conditional on those constraints, the gamma distribution provides the least information about it. And so that was seen by an attractive property by physicists and other people who were influenced by information theory, which has a lot of connections to probability theory, in particular by Ed James. Yes?
So when frequencies actual likelihood, they are unknowingly assuming gamma distribution around the parameter?
It's sort of a revisionist reinterpretation. You can interpret a maximum likelihood solution as a posterior mode if you let nu and chi approach 0. Now, that's not how frequentists think, but that's how we can sort of interpret frequentists as thinking, assuming they were doing something that made sense. Now, letting nu and chi go to 0 results in an improper gamma distribution. So that you can't really believe that. But mathematically, it's the same. All right? So, I mean, we went through probability in like 3 weeks. And like I said, you probably need at least a semester. But, you know, if we'd spent more time on probability, then, you know, we wouldn't have gotten into the Stan language. And so you have to make trade-offs. But hopefully we've done enough examples to where you can do more examples on your own and you can get more comfortable working with all of these popular distributions, many of which come from the exponential family. Questions? Nope. Okay. So coming back to a topic we've talked about a little bit, let's say delta is some function of the data x, and it's some rule that says, okay, if the data turns out to be little x, we're going to make decision D. So like, if there's a recession, our decision is going to be if there is a recession, our decision is going to be that we're going to lower interest rates, something like that. And then let's define ourselves a loss function, which is going to depend on the true parameters theta and what decision we make. So this is a function that tells us our loss or our regret if we make decision delta when the true state of the world, the parameter, the world is actually governed by these parameters theta in a vector. And so what frequentists do is define a frequentist risk function, or what frequentists just call the risk function, R, which is the expectation over X of the loss function. So they're saying, okay, I have my decision function, I have my loss function, I'm going to take the expectation of the loss function over the distribution of X. And so that is an integral involving the loss function multiplied by the PDF of X integrated over X and conditional on the true values of theta. So given values of theta, I can integrate the loss function over X. That is my risk function as a function of theta. Now, it's important to recognize that these risk functions are conditional on theta, the parameters, and integrating over possible values of X. And that strikes, or should strike, a lot of people as weird, because X is something that if we get data on, we actually know what it is. And theta, we're never going to be completely certain as to what it is, because it's just this unknown parameters in our model. So we're conditioning on theta, which is the thing that we don't know, and we're integrating over X, which is the thing that it's in our capability of collecting data on. And that seems weird, and it is weird, but according to Neyman, this is a good approach, because we can choose some way of making decisions that gives us a lower bound on the risk function. And that lower bound holds irrespective of what theta is. So we can design a decision rule, procedures, ways of doing research, and we can bound our risk function, and that bound does not depend on what the true value of theta is or anyone's beliefs about what the true theta is. An example of one of these functions is like if we take the loss function that's equal to 1, if our confidence interval does not include the true parameter theta, and the loss function is equal to 0 if our estimated confidence interval includes the true value theta. Now, we don't know what the true value theta is, but we can specify that loss function. We can integrate it over the data generating process for X, and we can get a risk function whose expectation is 0.05 if we choose the size of the confidence interval appropriately. And so that's really what confidence intervals do. It's this risk function that's calibrated so that irrespective of what theta is, the risk is less than or equal to 0.05 if we're doing 95% confidence intervals. Now, that's weird because it's integrating over data, and it's a stupid loss function, like 1 if the thing is outside the confidence interval, 0 if it's in. It doesn't matter if it's like a big confidence, a wide confidence interval, or a narrow one. It doesn't matter if you're just a little bit outside it or way outside it. It doesn't matter if the thing is, the true parameter is right in the middle of your confidence interval or shifted over. It's just, you know, 1s and 0s either way. That's what allows us to say, you know, the type 1 error rate is going to be 5% irrespective of what theta is. So that is really the essence of the frequentist approach, specifying weird loss functions, integrating them over the wrong thing and saying, if everybody were to follow this, you know, we're only going to mess up, we're only going to make type 1 errors 5% of the time across studies. But one of the problems that is, you know, well understood within the social sciences is it doesn't do a whole lot of good to specify these like rules or procedures that says, if everyone does things this way, then, you know, we're only going to make a type 1 error 5% of the time, when in each individual study, the incentives to not do things that way are too strong. You have to have some enforcement mechanism, which really doesn't exist, in order to get people to consistently follow the rules. And so in reality, like the incentives to publish and stuff like that are such that, well, if you have to throw away a few outliers to get the result that you want, you know, no one's really going to know. That messes up the whole procedure by which we derived a 5% type 1 error rate. Or, you don't get the results you want the first time, so you change the model. That messes up the 5% type 1 error rate, etc. And so there's all these incentives in the, each individual study that go against the rule that is sort of Neyman thought he was putting in place in order to ensure that sort of research has a bounded risk across a bunch of studies. So what Bayesians do is specify a Bayesian risk function, which Bayesians just call the risk function, which is the expectation of the loss function. Could be the same loss function, could be a more appropriate loss function, should be a more appropriate loss function. But we're going to take the expectation of that loss function over the conditional distribution of theta, which we don't know, given x, which is data that we do know. And so that is the integral loss function multiplied by PDF of theta given x integrated over the dimensions of theta. And so that gives you a posterior risk function. So sometimes you'll hear posterior risk function, sometimes prior risk function, where the posterior is replaced by a prior distribution on theta, not conditional on x, etc. But in any event, Bayesians are going to integrate over the parameters conditional on the data, which is the way more intuitive way to approach, expected loss. So Abraham Wald, who was actually at Columbia during the Great Depression and World War II, and then died in a plane crash. But before he died in a plane crash, he was a dyed-in-the-wool frequentist who happened to have more integrity than people like Fisher. And so when he discovered, first in a paper in 1939 and then in a book he wrote in 1950, that all rules, delta, for making decisions fell in three buckets. They were Bayesian, they were the limit of a Bayesian decision rule as the sample size goes to infinity, or they were worse than some Bayesian decision rule. And worse means dominated, dominating meaning the risk is no better than some Bayesian decision rule for any value of theta, and it's worse than that Bayesian decision rule for some value of theta. So nobody knows what theta is, but we do know that these non-Bayesian decision rules can be dominated by a Bayesian one, which means the Bayesian one is at least as good always and sometimes better, at least for some value of theta. And so that led him to a very Bayesian conclusion about the right way to make decisions in light of data. Now there's still a lot of wiggle room here as to what Bayesian decision rule you choose. There's lots of them. Or what decision rule you choose and how you go about doing it. But it basically says, do you want to make a decision, take an action as a result of doing your study, even if the action is so trivial as like, I'm going to believe that the world is round now, or I'm going to believe in global warming. Just like a personal decision as to what to believe around the world. The way to do that is by taking the expectation of some loss function over the posterior distribution not over the data generating process. Questions? Okay, so some examples of that, which we actually talked about the first day, but we didn't really go into the details about them. So say the decision you want to make is what point estimate should I use? Now that presupposes that you should use a point estimate. You don't have to. But if you're like forced to because you have to talk to some frequentist or something like that, they can only understand things. In terms of point estimates, you need to make a decision. What point estimate should I use? So the delta function results in some formula for constructing a point estimator of theta, which we'll call theta hat. So if your loss function between theta and theta hat, theta being the true beta, theta hat being your point estimate of theta, is their square difference, then we can take the expectation of that loss function over the posterior distribution by differentiating the loss function with respect to our point estimator and seeing what point estimator minimizes that risk quantity. So we have the derivative of the expectation of our loss function with respect to the posterior distribution of theta. For smooth functions like squared error, you can interchange the derivative and the integral sign. So the derivative of an integral is the integral of the derivative of the loss function with respect to theta hat. So squared error loss, the derivative of that is just 2 times the quantity theta hat minus theta multiplied by the posterior distribution, which involves the true theta, not theta hat. And we're going to integrate this over theta. So we do the integration. We get this 2 stuff, add and subtract, set that equal to 0. The 2's don't matter. And we get theta hat minus the expectation of theta conditional on x is equal to 0. And that implies the point estimator that minimizes squared error loss over the posterior distribution is the posterior mean. And squared error loss is oftentimes thought to be a pretty reasonable loss function. But what people have difficulty with is taking that loss function and doing the expectation over the posterior distribution. Because you first have to get the posterior distribution before you can figure out what the posterior mean is. And a lot of people are like, well, that's too much work, so I'll choose a dumber loss function. So another loss function, not necessarily a dumber one, is absolute error loss rather than squared error. In which case you go through the mechanics of this, not too hard, find the posterior median minimizes the expected loss of that loss function over the posterior distribution. Still got to get the posterior distribution or draws from it, but if you have that, you can calculate the posterior median just as easily as you can calculate the posterior mean. Well, that still requires that you get the posterior distribution. So is there an even dumber loss function that I could use? And unfortunately, there is. So if the loss function is equal to 1, if the true parameter is different from the point estimate, and the loss function is equal to 0 in the measure 0 case that theta is exactly equal to the point estimate, then it can be shown that the posterior mode minimizes the expectation of that loss function. And so that's where I say that the optimum, in the sense this minimizes the expected loss function, is the posterior mode, is suboptimal, because if you're making decisions off a binary loss function, you're going to do all kinds of ridiculous things. Even still, it sounds like you have to find the posterior mode, and that's too much for a lot of people. So they just find the mode of the likelihood, ignoring the priors, or something like that. But this sort of shows that you really need to get the whole posterior distribution in order to make reasonable decisions in light of data. However, if you go throughout Columbia, you go all kinds of other universities, optimization, which is to say find the mode of some function, is the only way that's taught how to approach quantitative analysis in most departments, at most universities, at most levels of education. They're only teaching optimization as the solution to quantitative problems. Maximum likelihood, find the maximum of a likelihood, whatever. Least squares, choose the parameters that minimize the sum of squared errors. Engineering, all kinds of things, whatever operational research, no, OR, what's that stand for? Operations research. They just do optimization problems all day long. And optimization is not a good way to make decisions in light of data. Conditional on the data, you're going to want some function of the whole posterior distribution, not just the mode, in order to minimize reasonable loss functions. So we'll pick it up on Thursday. We'll talk more about stuff, including some, more things on missing data. The thing I posted on Piazza. We'll also go over some hierarchical modeling stuff, etc. All right. Yeah.